Okay, so section 10.4 has to do with acid and base strength. And the first thing that we'll address is breaking acids and bases down into two categories: strong acids and bases and weak acids and bases. So a strong acid, when it reacts with water, something like HCl plus H2O, is going to react to completion. So I'll draw a single-headed arrow here. That's going to form the H3O plus Cl minus. And that means that at the end of the reaction there will be, 0% of this and 100% of that. Sodium hydroxide would be an example of a strong base. NaOH, when you put it in water, is going to break up into Na plus and OH minus. Again, 0% over here, 100% over there. So these are what we'll call our strong acids and bases. And there are only 6 strong acids listed in your textbook, so I'll just list them right here. H2SO4, HNO3, HClO4, HI, HBr, and HCl. So HClO3 is also sometimes considered a strong acid. It's really on the boundary between what should be considered a strong or a weak acid. The strong bases are soluble hydroxide salts. So if you think back to our solubility rules, that's group 1 hydroxides, sodium hydroxide, lithium hydroxide, potassium hydroxide, and then heavy group 2 hydroxides. So barium hydroxide, strontium hydroxide, and then calcium hydroxide is kind of on that border as well. But calcium hydroxide is usually considered a strong salt. A strong base. So these are the strong acids and bases. Weak acids and bases are going to reach equilibrium when they react with water. So let's do HNO2. Nitric acid is a strong acid, but nitrous acid is weak. Oops. I need the water in there, sorry. So HNO2 plus H2O. This is going to reach an equilibrium with H3O plus and NO2 minus. And the equilibrium is probably going to be highly reactant favored. So the particular numbers will be different from one acid to the next. So I'll say maybe this is about 5%, and this is about 95%. Weak bases are the same. If I have something like CO3 2 minus plus H2O, then that is going to form HCO3 minus and OH minus. Again, it's going to reach equilibrium, and that equilibrium will most likely be highly reactant favored. About 5% here and about 95% there. So these are the weak acids and bases. And strong acids and bases are all pretty much the same because they're all going to form 100% H3O plus. Between these 6 strong acids, if you need to do some acid-base chemistry, most of the time you could pick any one of the 6 and get identical results. But for weak acids and bases, some of them might be more like 10 or 15% product. Those would be weak acids that are sort of on the stronger end of the weak acids. And some of them may be as low as 1%. Those are truly very weak acids. And And so we'll talk about the strength of acids and bases, and in a minute we'll do that quantitatively with numbers. But I want to point out that just like before, every reaction is going to have a conjugate pair. Let me go ahead and erase this up here. And if I identify nitrous acid and nitrite ion as a conjugate pair, then their strengths are linked. The acid strength of nitrous acid and the basic strength of nitrite ion are linked together, such that the stronger this one is, the weaker its conjugate will be. The weaker the acid is, the stronger its conjugate base will be. And so let's look at a figure here. So this is table 10.2, and it shows a number of conjugate acid-base pairs. Let me see if I can... Nope. Sorry, I was trying to see if I could make it show my cursor. I don't know if you can see that or not. But we'll just start at the top. Perchloric acid's conjugate base is perchlorate ion. Sulfuric acid's conjugate base is the hydrogen sulfate ion, and that looks like it's a typo. That should be just HSO4-. Hydroiodic acid's conjugate is an iodide ion. For these 6 strong acids, because the acids are strong, that means that their conjugate bases are so weak that they're really not bases at all. This table says little or no reaction as bases. So the conjugate to a strong acid is technically a conjugate base, but it's really a base in name only, and it will not have any basic reactivity. And then you'll notice the hydronium ion itself is going to separate the weak acids from the strong acids. Let's look in sort of the middle of the weak acids. There we have the nitrous acid. Its conjugate is the nitrite ion. And the nitrous acid is kind of just barely on the strong side of the weak acids. And so you'll notice nitrite is labeled as a very weak base. Moving further down, about halfway through the very weak acids is hydrocyanic acid, HCN. Its conjugate, CN-, is a weak base, but it's on the stronger end of the weak bases. Because hydrocyanic acid is a very weak acid, then cyanide ion is a relatively strong member of the weak bases. And then all the way down at the bottom here, we've got the hydroxide ion, which is sort of all of our strong bases just generate hydroxide ion because they are soluble salts of hydroxide. So they have this relationship where every acid-base conjugate pair is going to be, the stronger one of them is, the weaker its conjugate partner is. Sorry, give me a sec here. Okay. So let me erase this. We'll leave up that nitrous acid reaction. And I should add the phases. So nitrous acid is aqueous. Water itself is liquid. Hydronium ion is aqueous. And the nitrite ion is aqueous. And so because this is an equilibrium reaction, we can talk about its equilibrium constant. K is going to equal the concentrations of the products, so that would be H3O plus, raised to the power of their stoichiometric coefficient. So that's just raised to the first power, the nitrite NO2 minus. And then we'll divide that by the concentrations of the reactants. So HNO2, or nitrous acid. And because water is a liquid, it actually doesn't appear in the equilibrium expression. Because this is an acid, then we'll call this a Ka, or the acid strength constant. So the acid strength constant is simply the equilibrium constant for the reaction of an acid with water. Not just any old reaction that involves this acid, but specifically its reaction with water is going to have an equilibrium constant that's equal to the Ka. You could sort of generalize this and say that the Ka for any acid is going to be the concentration of H3O plus times the concentration of A minus over the concentration of HA, where whatever your acid is, this will be its conjugate base, that's the conjugate acid, and H3O plus. So that is the acid strength. We could talk about a base reaction. So let's do ammonia. NH3 aqueous plus water, and that's going to form NH4 plus aqueous plus OH minus aqueous. And so the K, or the equilibrium constant for this base reaction, Kb, is going to equal NH4 plus times OH minus over NH3. Or again, if we want to generalize this, then we'll usually say this is HB plus OH minus and G, the base itself. So these equilibrium constants will tell the strength of the acid. Remember, the larger the value of K, the more product there is. And so a product-favored reaction would have an equilibrium constant greater than 1. Well, for all of our weak acids and weak bases, K is going to be less than 1, and it's just a question of how small it might be. So let's look at, sorry, let me advance here to the right figure. Okay, table 10.3 is going to give you some Ka values for a number of different weak acids. You'll notice some of them are very, very small indeed. Something like at the very end, HCO3 minus has a Ka value of 5.6 times 10 to the negative 11th. Others are relatively large. Under sulfuric acid on the right side, you'll see HSO4 minus with a Ka value of 1.2 times 10 to the negative second. So I want you to notice that sulfuric acid, phosphoric acid, and carbonic acid are multiprotic acids, and each step has its own Ka value. So sulfuric acid, H2SO4, was actually listed as one of our 6 strong acids. And so giving up its first proton, it will do that 100%. The Ka value they list here is just large. And there is a real value. I don't know what it is. It's probably tens or hundreds or something like that. But the second hydrogen is not given up quite so readily. It has a Ka value of 1.2 times 10 to the negative second. If you look at phosphoric acid, H3PO4, the first hydrogen is given up with a Ka on the order of 10 to the negative third. The second hydrogen is given up with a Ka on the order of 10 to the negative eighth. And the last one is given up with a Ka on the order of 10 to the negative 13th. And so you'll notice, and carbonic acid follows a similar trend. 10 to the negative 7th for the first, 10 to the negative 11th for the second. So you'll notice that each proton has its own Ka value, and it becomes successively more difficult to remove a proton on a polyprotic acid. So it'll always give up the first hydrogen more readily than it gives up the second, and more readily for the second than it does for the third. Likewise, we can, since we know that conjugate bases and acids have this inverse relationship in their strength, then we know that phosphate ion is the strongest base, and dihydrogen phosphate is the weakest base in that series. As I say that, I'm realizing that it's not going to make much sense to you unless I write that out on the board. So we'll go ahead and do that. So H3PO4 can be in equilibrium with H2PO4 minus, which is in equilibrium with HPO4 2 minus, in equilibrium with phosphate itself, PO4 3 minus. Now let's talk about acid-base properties of each of these different members of the polyprotic acid series for phosphoric acid. First of all of these, let's rank their acid strength. So phosphoric acid is the strongest acid. H2PO4 is the middle acid. We were just looking at their Ka values, right? And then HPO4 2 minus is the weakest acid. PO4 3 minus does not have any hydrogens left to give. So this is not an acid at all. Not an acid. So we can look at how the conjugate base to HPO4 2 minus is phosphate. If this is the weakest acid, then that must mean phosphate is the strongest base. Strongest base in this series. And then HPO4 2 minus is the conjugate base to the middle acid, so this must be the middle base. And then H2PO4 minus is the conjugate to the strongest acid in this series, so it must be the weakest base in this series. And H3PO4 is not a base at all. It will not accept a proton at all. Okay, so each different species in a polyprotic series has its own Ka value, and we can infer from that that each of them also has its own Kb value, and their relative strengths are inverted in this way. Okay, I think we'll stop it right there for acid strength.